Tonight, we're going to explore one of the most intellectually demanding space missions in human history. This is BepiColombo, a silent voyager bound for the scorched frontier of Mercury. To reach this iron planet, the probe has traveled a staggering 9.3 billion kilometers, more than 100 times the actual distance from Earth to its target, to grasp the precision required. Imagine shooting a microscopic speck of dust from Los Angeles, aiming it perfectly through a moving wedding ring on a race car speeding through New York. It leaves us with a fascinating question: why must a spacecraft take such an immense, looping detour just to reach a destination so close to home? Settle in and let the day fade. By the end of tonight, we will journey together through the unimaginable odyssey of BepiColombo. Before we dive in, if you share our passion for drifting through the cosmos, please take a moment to like this video or subscribe. It's a small gesture, but it goes a long way in helping this channel connect with more inquisitive souls like yourself. Welcome, and let the mind rest as the story unfolds. We travel back to the ancient city of Padua, Italy. Imagine walking along quiet, moonlit cobblestones, passing beneath the vaulted stone arches of a university that has stood for over 8 centuries. This is a place where history breathes from the very walls. It is the very institution where Galileo Galilei once stood by a tall, arched window, adjusting his early telescope to gaze at the moons of Jupiter. In this deeply intellectual atmosphere, the foundations of how we understand the heavens were laid down decades ago in the middle of the 20th century. Another brilliant mind walked these exact same paths, breathing in the same quiet night air. His name was Giuseppe Colombo, known affectionately to his colleagues and later to the world of space science simply as Bepi. Born in 1920, Colombo was a man who truly belonged to a different, more deliberate era. He was a professor of mechanical engineering, a thinker who belonged to a noble lineage of classical scientists. In our modern world, we are accustomed to massive supercomputers, glowing digital screens, and complex algorithms that simulate the cosmos at the touch of a button. But BepiColombo worked in a simpler, perhaps more beautiful time. His tools were not silicon microchips or blinking servers, but a sharpened graphite pencil, stacks of yellowed paper, and a grand slate chalkboard covered in white chalk dust. He believed that the human mind, when guided by the elegant laws of mathematics, could see further into the dark than any machine ever built. He had an innate ability to look at a sheet of numbers and see a physical reality. To watch him work in the evening was to witness a master craftsman of the mind. He would spend quiet hours under the soft, warm glow of a desk lamp, filling pages with dense rows of numbers and equations. He was entirely obsessed with the intricate cosmic clockwork. He spent his life studying celestial mechanics, which is simply the branch of astronomy that deals with the mathematical laws and forces governing how planets, moons, and stars move through the emptiness of space, where others saw chaotic, unpredictable paths in the night sky. Colombo saw an exquisite, predictable ballet. He understood that every planet was bound by invisible gravitational strings, pulling and tugging on one another in a delicate balance that had been playing out for billions of years across the dark. For Colombo, solving a profound problem about a distant, unreachable planet did not require launching a multi-million-dollar rocket. It required an absolute, unquestioned mastery of geometry and physics. He looked at the solar system as a vast, interconnected machine, much like the fine grandfather clocks that tick dependable seconds in our living rooms. This classical approach meant that he could anticipate natural phenomena that larger institutions, with all their funding and new age electronics, had completely overlooked. He possessed a rare, intuitive feel for gravity, treating it not just as a cold formula on a page, but as a living current in the void, a cosmic river that a clever traveler could ride across the dark ocean of space. For decades, the global scientific community looked toward Mercury and believed they understood its most fundamental nature. The established consensus, backed by early radar measurements and the heavy weight of scientific authority, was that Mercury was trapped in a state of one-to-one tidal locking. This meant astronomers believed the planet took the exact same amount of time to rotate once on its axis as it did to complete a single journey around the Sun. It was an idea that seemed perfectly logical, mirroring how our own moon faces the Earth, forever hiding its dark side from our view. Under this old theory, Mercury was imagined as a world of brutal, static extremes. Scientists pictured a planet split into two distinct halves, a permanent day side, forever baked under the terrifying, unblinking glare of the solar furnace, and a permanent night side, locked in eternal, freezing darkness. It was a bleak, unmoving vision of a celestial body frozen in time. But in 1965, from his quiet study in Italy, BepiColombo began to look closer at the mathematics governing this distant rock. He sensed that nature was rarely so simple or so rigid. With his characteristic patience, Colombo began to analyze the slight gravitational tugs and the oval shape of Mercury's orbit. Through pure mathematical deduction, he uncovered a beautiful truth that shattered the old consensus. He discovered that Mercury was not locked in a simple one-to-one embrace. Instead, it was participating in a far more complex and elegant phenomenon known as orbital resonance, which is the perfect synchronized dance between a planet's rotation on its axis and its orbital journey around its host star. Colombo proved that Mercury's resonance was not one-to-one, but rather a unique 3-to-2 ratio. This meant that the planet rotates exactly 3 times about its own axis for every 2 complete revolutions it makes around the Sun. To the scientific world, this was a stunning revelation, a complete mathematical turn that rewrote the textbooks. It transformed our understanding of Mercury from a static, half-dead rock into a world of dynamic, shifting rhythms. This 3-to-2 rhythm creates a concept of time that stretches the human imagination. Because of this unique synchronization, a single solar day on Mercury, the time it takes for the Sun to rise, cross the sky, and set again, actually lasts for 2 full Mercury years. Imagine a world where a single day takes twice as long to finish as the entire year itself. A resident of that planet would experience 3 full nights and 3 full days over the span of 2 orbital journeys. The Sun would appear to rise, slow down, stop in the sky, and even move backward for a brief period before continuing its slow march across the horizon. By uncovering this elegant mathematical law, BepiColombo did more than just correct an error in astronomy. He brought a sense of poetic harmony to a place that once seemed chaotic and brutal. He showed us that even in the extreme environment closest to our star, Gravity does not simply crush a planet into a frozen posture. Instead, it coaxes it into a beautifully complex, rolling waltz. Back to the early years of the 1970s, this was a golden era of space exploration, a time of profound curiosity when humanity was first taking its bold, tentative steps into the deeper waters of our solar system. At the Jet Propulsion Laboratory in Pasadena, California, the brightest minds in aerospace engineering were gathered around large drafting tables, working on a mission known as Mariner 10. Their goal was ambitious: to send a robotic scout to look upon the face of Venus, and then, for the first time in history, to journey to the absolute innermost planet, Mercury. Yet, the brilliant engineers at NASA faced a disheartening constraint. The physics of rocket travel in those days were brutally rigid. Liquid chemical fuel was incredibly heavy, and every additional pound of propellant meant a larger, more expensive rocket. According to all standard calculations of the time, Mariner 10 would only have enough onboard energy to make a single, fleeting pass over Mercury. It would be a one-shot mission. The spacecraft would rush past the planet at immense speed, snap a few hasty photographs of one hemisphere, and then be pulled helplessly into the vast, dark void surrounding the Sun, never to return to the scientific community. It felt like a tragic compromise, a brief, tantalizing glimpse of a world that would immediately slip back into the shadows. It was during this period of quiet frustration that our solitary Italian professor, BepiColombo, arrived at the laboratory as a visiting consultant. He sat quietly in the back of the briefing rooms, a gentle contrast to the fast-paced, high-stress environment of American big-budget engineering. He did not look at the problem through the lens of brute force or larger fuel tanks. Instead, he looked at it with the graceful intuition of a classical geometer. Colombo requested the raw data sheets and the preliminary flight paths. Sitting at a simple desk, away from the hum of the early mainframe computers, he began to sketch out a series of elegant loops with his graphite pencil. As he analyzed the proposed trajectory, Colombo noticed a beautiful mathematical coincidence that everyone else had overlooked. He realized that the spacecraft did not have to accept a terminal, one-way destination. He walked up to the NASA engineers and presented a concept that would fundamentally change the history of interplanetary flight. He introduced them to the delicate art of the gravitational slingshot, which is the artistic method of using the intense pull of a planet's natural gravity to alter the speed and direction of a traveling spacecraft without expending a single drop of precious fuel. Colombo argued that if NASA could guide Mariner 10 past the heavy mass of the planet Venus at an incredibly precise, predetermined angle, the gravity of Venus would act as a gentle cosmic brake, bending the spacecraft's path and slowing it down just enough to drop it into a highly specific orbital loop around the Sun. But his genius did not stop there. He calculated that this new solar orbit would possess a magical property. Its timing would be perfectly synchronized with Mercury itself. Every time the spacecraft completed one full loop around the Sun, Mercury would arrive at the exact same point in space at the exact same moment. Initially, the engineers at the laboratory were deeply skeptical. The idea that a foreign professor could sit down with a piece of paper and suddenly multiply the value of a multi-million-dollar space mission seemed almost like a parlor trick. It felt like trying to get something for nothing from the universe. However, they dutifully fed Colombo's handwritten equations into their room-sized computers. For hours, The magnetic tape reels spun in the quiet rooms, processing the mathematics. When the printouts finally emerged, the data confirmed the professor's calculations with absolute certainty. The math was flawless. NASA immediately tore up their old flight plans and adopted Colombo's visionary design. When Mariner 10 launched into the evening sky in late 1973, it carried with it the quiet thoughts of the professor from Padua. The mission achieved a level of success that had previously been deemed impossible. Instead of a single, hurried glance, the spacecraft successfully returned to Mercury a total of 3 distinct times between 1974 and 1975. It mapped nearly 45% of the planet's rugged surface, discovering its unexpected magnetic field and providing humanity with its first real understanding of that lonely, sun-baked world. This historic triumph did more than just save a single mission. It gifted humanity a new way to sail across the cosmos. It proved that we do not need to fight against the immense forces of gravity. We simply need to understand them, to lean into them, and let the planets themselves carry us across the dark. When we look up at the night sky on a clear evening, our human intuition tells us a very simple story about travel. We imagine that the hardest places to reach must be those that are the farthest away, hidden in the dim, frozen outer rims of our celestial neighborhood. We look at Pluto or the beautiful rings of Saturn, and we assume that because they require years of travel across billions of miles, they must demand the greatest effort from our machinery. Conversely, when we look toward Mercury, the innermost planet, it appears tantalizingly close. It is practically next door to Earth when compared to the vast, lonely distances of the outer worlds. Yet, in the realm of space exploration, this closeness is a profound and beautiful deception. To understand why a voyage to this tiny world is so difficult, we must discard our earthly notions of travel and step into the elegant, counterintuitive laws of orbital physics. In space, journeys are never measured in linear miles or kilometers, but in the sheer amount of energy required to alter a spacecraft's path. When a contour leaves the safety of Earth, it inherits our planet's immense speed as we orbit the Sun. We are all moving together at a tremendous velocity. If a spacecraft wants to travel outward, away from the Sun, toward Mars or Jupiter, the journey is akin to climbing a long, gentle hill. You must add energy, firing your rockets to push yourself up and out against the Sun's pulling force. It is a long haul, but a straightforward one. However, when you turn your eyes inward, toward the blinding light of the solar center, the entire landscape changes. Traveling to Mercury is not a matter of climbing a hill. It is a matter of stepping off a steep, precipitous cliff. As soon as a vessel drops toward the center of the solar system, it enters the most formidable territory in our cosmic neighborhood. This brings us to a fundamental concept that lies at the very heart of our story, the gravitational potential well, which is simply a giant, invisible funnel in the fabric of space and time, created by the staggering mass of the Sun, pulling everything toward its crushing, bright center. Imagine a massive bowling ball resting in the center of a large, tightly stretched rubber sheet. The heavy ball creates a deep, steep depression, a downward sloping bowl that acts as an inescapable trap for anything that ventures too close. The Sun, containing over 99% of all the matter in our entire solar system, creates a cosmic well so deep and powerful that its influence dominates everything for billions of miles. Earth sits safely on a stable, high ledge near the rim of this giant funnel, balanced perfectly by our forward momentum. But to send a scout like BepiColombo down into the depths of that funnel to visit Mercury requires an extraordinary and terrifying amount of control. As the spacecraft drops toward the sun, the steepening slopes of this gravity well begin to act upon it with immense ferocity. The sun's gravity takes hold of the vessel, pulling it downward, faster and faster, transforming the journey into a runaway train ride down a mountain. Herein lies the great, beautiful paradox of Mercury exploration. To reach a planet that is relatively close to home, a spacecraft actually requires far more energy than a mission sent to the absolute edge of the solar system. In fact, it takes more sheer effort to successfully insert a satellite into a stable orbit around Mercury than it does to escape the sun's gravity entirely and leave the solar system forever. If a Contao were to fly straight toward Mercury without a plan, the sun would accelerate it to such an extreme velocity that it would streak past the tiny planet like a flash of lightning, unable to stop before being incinerated by the solar furnace. The barrier to Mercury is not a barrier of physical distance, but a barrier of dynamic velocity. It is an invisible wall built out of the sun's overwhelming desire to pull everything into its core. As BepiColombo journeys downward, it is constantly fighting against this acceleration, trying desperately not to slide too fast into the abyss. It must find a way to shed that terrifying speed, to apply a steady, continuous brake while navigating a path that spirals gracefully along the walls of the funnel. Let us rest our minds for a moment on a technology that many of us grew up admiring: the roaring, majestic power of the traditional chemical rocket. For generations, this was the ultimate symbol of human ingenuity and mechanical prowess. We well remember the grand launches of the Apollo era, the towering Saturn vehicles venting sheets of white frost against a blue sky, and the thunderous, earth-shaking roar that followed their awakening. These machines operated on a principle that feels deeply familiar to anyone who loves classical mechanical engineering. They are, at their core, magnificent internal combustion engines scaled up to cosmic proportions by mixing liquid fuel, such as highly refined kerosene or liquid hydrogen, with an oxidizing agent like liquid oxygen. They create a controlled, incredibly violent explosion. This explosion releases an immense amount of kinetic energy in a matter of minutes, pushing a spacecraft off the launch pad and forcing it out into the starry dark. This method of travel is brilliant for escaping Earth's heavy embrace, but when we try to apply this same brute force philosophy to the delicate task of orbiting Mercury, we run into an unyielding wall of physics. To navigate the vast celestial highway, aerospace engineers do not think in terms of simple miles per hour or gallons of fuel. Instead, they rely on a foundational metric known as delta phi, which is simply the total change in velocity, representing the exact amount of raw structural impulse required for a spacecraft to accelerate, brake, or shift its orbital path through the frictionless vacuum of space. Every maneuver in the cosmos, whether it is a slight steering correction or a massive deceleration burn, has a specific delta V cost. It is, quite literally, the currency of space travel, and some destinations are far more expensive than others. The Delta Vibe required to drop down into the Sun's territory and successfully match the speed of Mercury is monstrously high, because the Sun is continuously pulling the spacecraft downward into its deep gravitational funnel, accelerating it to terrifying speeds. The vehicle arrives at its destination moving far too fast to enter a stable, gentle orbit around the innermost planet. The spacecraft must perform a massive braking maneuver. It must shed kilometers of speed every single second. If we were to use a traditional chemical rocket for this task, we would need to flip the Contao completely backward and fire a large engine directly against our direction of travel, burning a massive amount of propellant to slow ourselves down to a safe, attachable speed. This is where we encounter what engineers call the tyranny of the rocket equation, a mathematical truth that completely breaks the spirit of traditional brute force engineering. The paradox is deceptively simple and entirely unforgiving. If you want to fire a heavy rocket engine at the very end of an 8-year journey to slow down, you must carry all of that heavy liquid fuel with you through every single twist, turn, and loop of the voyage. However, rocket fuel is incredibly heavy. To carry that heavy braking fuel away from Earth in the first place, you need to add even more fuel to your initial launch rocket, but that extra launch fuel adds more weight, which in turn requires even more fuel just to lift the fuel that was meant to lift the fuel. The mathematics do not climb in a straight, predictable line. They explode exponentially. To successfully slow a modest, multi-ton scientific probe down at Mercury using standard liquid rocketry, the sheer volume of fuel required at the start of the mission becomes completely absurd. The launch vehicle sitting on the pad at Earth would have to be larger than the greatest skyscrapers ever built, weighing millions of tons, almost entirely filled with propellant just to deliver a tiny camera and a few sensors to the final destination. It is a mathematical dead end, the largest and most powerful rockets ever conceived by humanity. From the historic Saturn vehicles to the modern heavy launchers, are rendered completely powerless by this fundamental law of mass ratio. They simply cannot carry enough chemical energy to fight the Sun on its own terms. This realization brought a profound sense of humility to the early planners of the Mercury mission. It forced them to accept that human might and explosive power have strict limits in the grand architecture of the cosmos. You cannot conquer the deepest gravity well in the solar system by simply burning more oil or building a bigger fire. The traditional methods that successfully carried us to the moon are fundamentally helpless against the sheer, crushing scale of the Sun's gravitational trap. It is a beautiful reminder that the universe cannot be bullied into submission. It must be understood, and its own natural laws must be turned to our advantage. When human muscle and explosive chemical rockets proved utterly helpless against the crushing grip of the Sun, the architects of this mission did not despair. They laid down their heavy wrenches, stepped away from the roaring test stands, and turned instead to the quiet, sublime beauty of pure geometry. They realized that to conquer the solar system's steepest gravitational slope, they could not fight nature with brute force. Instead, they would have to dance with her. They designed an unimaginable path, a majestic, looping detour stretching across 9,300,000,000 kilometers, transforming what should have been a straightforward sprint into a long, patient, 8-year celestial ballet. This exquisite journey relies entirely on a magnificent trick of orbital mechanics, a concept that turns our everyday understanding of navigation completely upside down, to slow down their multi-ton traveling laboratory. The navigation team utilized a precise physical maneuver known as a retrograde gravity assist, which is the calculated art of braking by steering a spacecraft directly ahead of a planet's moving orbital path, allowing that planet's massive natural pull to act as an invisible anchor that drags the vessel backward and quietly drains its excess kinetic energy. While traditional deep space missions use the gravity of heavy worlds like Jupiter to whip themselves forward into hyperdrive, BepiColombo does the exact opposite. It uses the inner worlds as a series of colossal natural friction brakes, gently shaving off miles per second from its speed every time it brushes past a planet. Imagine the immense patience required to choreograph this 8-year mechanical waltz across the dark. The journey began with a single, sweeping return to our own home world. In April of 2020, as the world below slept, BepiColombo silently skimmed just thousands of miles above the upper fringes of Earth's atmosphere, bidding a final quiet farewell to its creators, while letting Earth's familiar gravity gently nudge it inward toward the sun. From there, the lonely explorer plunged into the thick, cloud-shrouded domain of our sister planet, Venus. It encountered this brilliant, hostile world once in October of 2020 and again in August of 2021. Each close encounter with Venus acted like an invisible parachute, slowing the spacecraft down and reshaping its wide, oval path into a much smaller, tighter circle that dropped it deeper into the sun's blinding territory. Having survived the heavy embrace of Venus, the spacecraft finally arrived at its target, but it was still traveling far too fast to stay. It had to begin a grueling series of 6 individual flybys of Mercury itself. Think of it as a master sailor performing a sequence of sharp, elegant tacks against a powerful, blinding gale. The first 3 flybys occurred between 2021 and 2023, with each pass bringing the spacecraft closer and closer to the true rhythm of the innermost world. By the time it completed its 4th and 5th flybys in the later years, the spacecraft was performing an intricate game of cosmic tag, brushing past the rugged, cratered gray plains of Mercury at distances closer than a commercial airliner flies above the Earth. The sheer precision required to execute these 9 planetary encounters is almost impossible for the waking mind to grasp. As BepiColombo glides through the frictionless void, it must hit specific entry points in space that are only a few hundred meters wide. After traveling millions of miles through the dark, if the spacecraft approaches just 1 fraction of a single degree too high, it will miss the planetary break entirely, overshooting its mark and sailing helplessly into a permanent orbit around the sun, where it will eventually be baked into a useless piece of drifting metal. If it dips just a hair too low, the immense gravitational pull will drag it down into a catastrophic, high-speed collision with the planet's unyielding crust. Yet, month after month, year after year, the navigational teams on Earth monitor the telemetry, adjusting the path with silent, unhurried confidence, letting the laws of Isaac Newton and Albert Einstein guide their hand. There is a profound, meditative peace in this method of travel. It is a journey that cannot be rushed by human impatience or political demands. It demands that we submit completely to the steady, unyielding clockwork of the cosmos. As you listen to the steady, rhythmic cadence of this story, picture BepiColombo as it exists right now in this very year of 2026. Having completed its final breathtaking flybys, it has shed the terrifying velocity of its initial fall. It is no longer rushing frantically. It has matched the slow, deliberate stride of its target. Let your mind drift alongside this magnificent piece of human craftsmanship. See it gliding silently through the velvety black void, backlit by the immense, quiet glow of the sun, perfectly balanced between the gravitational currents of the inner solar system. The hard work of the journey is done. The 9 billion kilometers of braking are complete. The spacecraft is resting in its final graceful coast, waiting for the gentle hands of Mercury's gravity to permanently cradle it into orbit this coming November. To survive this elegant but punishing celestial ballet, humanity could not rely on standard aerospace design. The magnificent geometric path carved through the dark required an equally extraordinary vehicle to endure it. We must now turn our attention from the invisible currents of gravity to the physical marvel of the machine itself, peering beneath its protective armor to dissect a unique 3-in-1 masterpiece of harmonious engineering. To understand BepiColombo, one must appreciate the sheer genius of its physical form. It does not look like a traditional, single-bodied satellite. Instead, it is a magnificent masterpiece of mechanical packaging, a brilliant 3-in-1 modular architecture that challenges everything we know about how a deep space probe should be built. Before this vessel could begin its journey across the solar system, it had to face the rigid, unyielding constraints of Earth-bound rocketry. The nose cone of a heavy launcher, specifically the formidable Ariane 5 rocket, presents an uncompromisingly tight cylinder of space. Every square inch is precious. The engineers were faced with a daunting puzzle. They needed to send 2 completely separate scientific satellites, built by 2 different space agencies from opposite sides of the globe, all the way to Mercury. Building 2 separate rockets was economically impossible. The solution they devised was as daring as it was elegant. They decided to stack 3 independent components directly on top of one another, locking them into a single, tightly integrated column that could fit snugly beneath the rocket's protective fairing. This brings us to a beautiful concept in aerospace engineering known as the spacecraft cruise configuration, which is simply the unified mechanical arrangement of multiple individual modules locked together into a single, cohesive structure during the long, multi-year journey across the solar system. For 8 long years, BepiColombo has traveled not as a collection of loose parts, but as a single, towering mechanical entity. At the very base of this stack sits the heavy cargo hauler, the Mercury transfer module. Stacked perfectly on top of it is the European Space Agency's planetary orbiter, a sleek, silver craft designed to map the rocks below. And resting at the very summit, safely nestled inside a protective thermal garage, is the Japanese Space Agency's magnetospheric satellite. There is a profound, meditative philosophy behind this modular design. It represents an absolute triumph of cosmic symbiosis. In traditional engineering, we often think of independence as a strength, but in the unforgiving void of space, survival requires absolute cooperation during the long haul across the dark. The individual satellites do not operate as separate machines. They have surrendered their autonomy to the collective whole. The top satellites remain completely dormant, their advanced sensors turned off, their scientific eyes closed, and their solar wings folded tightly against their bodies, like hibernating birds. They do not need to worry about navigation, communication, or power generation. Instead, the entire stack shares a single, common umbilical cord of electrical lifeblood and data. The heavy module at the bottom acts as the dedicated provider, generating all the electricity from its giant solar arrays and doing all the heavy steering. The middle module acts as the central brain, handling all the communications back to the giant radio dishes on Earth. They fly together as a single heartbeat, an interlocking puzzle where the strengths of one module perfectly offset the vulnerabilities of the next. It is a design born out of necessity, but executed with the grace of a fine Swiss watch, where every latch, every spring, and every structural beam serves a dual purpose in this shared ecosystem. We have marveled at the grand geometry of the flight path and the elegant puzzle of the ship's modular design. Now, let us look down into the very base of the machine, into the engine bay of the Mercury transfer module, to witness the quiet powerhouse that made this entire journey possible. For generations, men who loved machinery were taught that power meant noise, heat, and raw, explosive violence. We grew up watching the great piston engines of the mid-century, the whistling turbines of jet aircraft, and the thunderous, fire-spewing rockets of the early space age. But the machine we are looking at tonight operates on a philosophy that is completely different. It is a technology of exquisite subtlety, a whisper in the dark rather than a shout, a brave heart that does not burn oil or kerosene, but gently coaxes a rare, noble gas across the void. Deep within the structural core of the module sit thick, spherical tanks forged from high-grade titanium. Inside these vessels lies the soul of the ship's propulsion system, a supply of pure xenon gas. For those who appreciate the quiet order of the periodic table, xenon is a magnificent choice. It is a heavy, noble gas, completely inert, meaning it refuses to react with other elements. It cannot catch fire, it cannot explode, it cannot corrode the metal that holds it. It simply sits in the dark, dense and perfectly peaceful, waiting for its turn to be transformed into kinetic life. This brings us to the technological marvel at the very center of our story, the electrostatic ion thruster, which is simply a highly sophisticated propulsion engine that uses intense electrical fields to accelerate charged atomic particles to extreme velocities, releasing them out of a nozzle to create a steady, continuous, and highly efficient push. Unlike a traditional rocket engine that uses a chemical fire to blast hot gas outward, this thruster uses the clean, silent power of electricity harvested from the sun. The giant solar wings of the spacecraft collect sunlight, converting it into an electrical current. This current is fed into a chamber where a tiny, meticulous stream of xenon atoms is released. The system strips away electrons from the xenon atoms, turning them into positively charged particles called ions. These ions are then focused by a sequence of high-voltage metal grids, which act like a powerful magnetic slingshot, accelerating the ions and shooting them out into the vacuum of space at speeds exceeding 30 kilometers per second. The most fascinating aspect of this technology is its gentle, almost meditative nature. The thrust produced by an individual ion engine is unbelievably faint. If you were to place your open hand directly over one of these thrusters while it was operating at its absolute maximum capacity on Earth, you would feel a force no heavier than a single sheet of standard writing paper resting on your palm. It possesses no brute strength, It cannot lift a feather against Earth's gravity, let alone a multi-ton spacecraft. But in the friction-free, weightless environment of deep space, where there is no air to resist motion, this feather-light whisper becomes a relentless superpower. A chemical rocket fires for a few minutes and exhausts its fuel. BepiColombo's ion engines do not run for minutes, but for thousands of hours at a time, day after day, month after month, year after year. It is the ultimate manifestation of the tortoise and the hare, an enduring, patient acceleration that accumulates over time until it achieves monumental results. It is this gentle, continuous push that has successfully acted as the 9 billion kilometer brake, slowing the spacecraft down as it slid into the sun's powerful gravity well. The absolute reliability of this system was tested to its very limits in the spring of 2024. The engineering team on Earth noticed a sudden, unexpected drop in the electrical current flowing from the solar arrays to the thrusters, a technical anomaly that threatened to derail the entire mission. In an older era of engineering, an engine failure meant a catastrophic breakdown, but because of the adaptable, digital nature of the ion thrusters, the engineers at the Mission Control Center in Germany did not panic. Operating from millions of miles away, they spent weeks calmly analyzing the telemetry, rewriting the software, and reorganizing the power distribution. They adjusted the firing schedules, allowing the engines to run at a lower, safer wattage while maximizing every single ion of thrust. This masterclass in remote troubleshooting proved the incredible resilience of the technology, ensuring that despite the drop in raw power, the ship stayed safely on its path to destiny. And now, we find ourselves at a moment of profound historical serenity. On the 15th of June in this current year of 2026, BepiColombo achieved a quiet milestone that marks the end of an era. Having completed its final tilts, critical deceleration maneuvers, and exhausted its planned supply of xenon gas, the brave ion engines of the module were officially powered down for the very last time. The soft, ethereal blue glow that had illuminated the nozzle for 8 years gently faded into the blackness. The engine has completed its magnificent, lifelong work. It has successfully reined in the spacecraft, taming its wild speed and bringing it to the exact velocity needed to meet its target. The Explorer is now resting, gliding on pure, unforced momentum, floating gracefully toward its final orbital capture this coming November. BepiColombo is not just a triumph of physics, it is a profound testament to international cooperation. A grand bridge built between the European Space Agency and the Japan Aerospace Exploration Agency. For decades, these two organizations developed their own unique engineering philosophies. The Europeans are known for their sprawling, incredibly intricate, and deeply methodical systems, while the Japanese possess a legendary eye for elegant minimalism, structural compacting, and unbreakable reliability. When tasked with exploring Mercury, they realized that a single spacecraft could never answer all the questions hidden on that iron world. They needed two completely different eyes in the dark, and to send them there, they had to merge their contrasting engineering souls into a single, cohesive entity. Let us first examine the European contribution, a sleek, silver vessel known as the Mercury Planetary Orbiter. This craft is designed with a singular, unwavering purpose to stare directly down at the rugged, scorched face of the planet below, capturing high-definition, three-dimensional imagery, and mapping the chemical secrets of the crust. To achieve this, the planetary orbiter requires absolute stillness. It utilizes a mechanical philosophy called three-axis stabilization, meaning it remains completely rigid in space, frozen like a statue relative to the world it is observing. This rigidity is governed by its attitude control system, which is simply the clever collection of sensors, computers, and internal reaction wheels that work in unison to keep a spacecraft perfectly oriented, ensuring it points its scientific cameras and communication antennas exactly where they need to go in the frictionless void of space. By constantly adjusting the spin of internal heavy metal flywheels, the European craft can fight off the slightest external tugs, keeping its scientific eyes locked onto the planetary surface with the unwavering focus of a master marksman. But nestled right on top of this rigid European statue sits a completely different creature, the Japanese contribution, poetically named MEO, or the Mercury Magnetospheric Orbiter. MEO's mission is not to look at the solid ground, but to feel the invisible, chaotic forces washing through space, the planet's magnetic field, and the violent streams of subatomic particles blowing off the sun. To measure these unseen currents from every possible direction, a stationary craft is useless. MEO needs to look everywhere at once. Therefore, the Japanese engineers designed it to use spin stabilization. Once it enters its final orbit, MEO will release itself and begin to spin like a top, rotating at a steady pace of 15 revolutions per minute. This constant spinning serves a brilliant dual purpose, acting as a masterclass in thermal management. In the intense heat near the sun, if one side of a spacecraft faces the glare for too long, it will melt, while the shadow side freezes. By spinning 15 times every minute, MEO distributes the solar heat perfectly across its entire body, much like a chicken turning slowly on a rotisserie over an open campfire, ensuring no single component ever reaches a critical breaking point. Herein lies the magnificent engineering paradox that the two space agencies had to solve together. How do you take a spacecraft that must remain perfectly still and rigid, and attach it to a satellite that is fundamentally designed to spin, and then fly them locked together through a brutal 8-year journey without tearing the structure apart or losing control of the flight path? If the Japanese craft were allowed to wobble or rotate even a fraction of a millimeter while attached to the European core, it would induce dangerous vibrations, confusing the navigational sensors and sending the entire mission spinning out into the cosmic void. The solution was a marvel of cooperative mechanical engineering. They created a specialized mechanical adapter, a heavy-duty structural interface that locks MEO into a completely rigid, motionless embrace for the duration of the long cruise phase. The Japanese craft agreed to remain completely silent, its spinning mechanisms locked down with heavy mechanical clamps, trusting its European host to guide it safely through the dark. As we look upon this vessel in this current year of 2026, we see the absolute beauty of this quiet compromise. For 8 long years, these two distinct machines, born from different languages and cultures on opposite sides of our planet, have flown as a single, flawless silhouette against the blackness of the solar system. They have endured the freezing cold and the blinding solar glare together, proving that when human beings unite their intellects, even the most contrasting engineering philosophies can dance in perfect symmetry. Now, let us turn our gaze slightly forward in time to a cold, magnificent evening in November of this current year, 2026, after traveling 9 billion kilometers through the unblinking dark. BepiColombo will finally arrive at the gates of Mercury. But arrival does not mean rest. Instead, it triggers the grand finale of this multi-year journey, an exquisite automated mechanical sequence that engineers affectionately refer to as the Grand Separation. For 8 long years, the 3 modules have flown as one single heartbeat. Now, in the absolute silence of the cosmic void, they must say goodbye. The opening act of this silent orbital drama belongs to the faithful workhorse at the base of the stack, the Mercury transfer module. This heavy cargo hauler has given everything it had to give. Its brave ion engines have officially fallen silent. Its titanium tanks are completely emptied of their precious xenon gas, and its massive 14-meter solar wings have completed their long harvest of sunlight. It has fulfilled its life's singular purpose. It has brought its precious cargo safely across the abyss and applied the great cosmic brake. Now, it has become an unnecessary burden, a heavy shell that would prevent the scientific probes from entering their proper orbits, with a series of silent, internal commands. The umbilical lines that shared electrical lifeblood across the modules are gently disconnected. To achieve this graceful parting of ways, the central computer triggers a highly specific engineering process known as pyrotechnic separation, which is simply the ultra-precise, millisecond-timed firing of miniature, highly stable explosive charges built directly into structural fastening bolts to cleanly cut the rigid mechanical joints holding separate spacecraft components together without sending harmful shockwaves through their delicate scientific instruments. In the profound silence of space, where there is no air to carry a roaring sound, this event happens in utter, ghostly quiet. The heavy metal joints snap instantly. Heavy-duty mechanical springs, which have been compressed under thousands of pounds of pressure since the launch pad on Earth, are suddenly released. They give the empty transfer module a gentle, unhurried push, sending it drifting away into a permanent, lonely orbit around the Sun, where it will slowly fade into the golden glare of history. With the heavy hauler gone, the remaining 2 satellites are now exposed directly to the harsh environment of Mercury, but the sequence is only half complete. Next comes the liberation of the Japanese satellite, Mio. For nearly a decade, Mio has been sleeping soundly inside its protective thermal garage, shielded from the blinding solar rays by a large, cone-shaped structure called the Sun Shield. Now, this protective cage must be discarded. Once again, tiny internal latches release their grip with mechanical perfection. The Sun Shield splits apart and is cast into the dark, floating away like a hollow chrysalis left behind by a butterfly. For the first time since leaving Earth, the gleaming, mirror-polished surface of the Japanese satellite is revealed to the vacuum of space, ready to feel the unseen forces of the cosmos. The European Planetary Orbiter and the Japanese Magnetospheric Orbiter, which have shared every mile and every hazard of the journey, must cut their final connection. The last mechanical hooks are disengaged, and internal springs push them apart with absolute gentleness. Moving at a speed slower than a human stroll, as they drift apart, they begin to assume their true, independent identities. The European craft fires its small chemical thrusters, gently lowering its height to settle into a low, circular path close to the rugged rocks below. Simultaneously, the Japanese satellite activates its internal systems, opening its long, thin wire antennas and beginning its long-awaited waltz, rotating at a steady pace of 15 revolutions per minute as it climbs into a sweeping, high elliptical path to map the invisible magnetic fields. There is a sublime, meditative beauty in watching this complex, mechanical divorce unfold entirely without human intervention, millions of miles away from home, with radio signals taking minutes to travel back and forth to Earth. No human engineer can push a button to guide these pieces in real time. The entire choreography must be executed flawlessly by the ship's internal memory, a testament to the decades of thought and planning that went into every single spring and bolt. As these two independent scouts part ways in the silence, they must immediately confront their ultimate adversary, the unblinking, terrifying glare of the solar forge. Stripped of their shared protection, each separate machine must now rely on its own specialized armor. The challenge shifts from the precision of mechanical movement to the absolute limits of material survival as they prepare to plunge into the heart of a blinding cosmic kiln. When we look at images of deep space probes, our minds often recall the familiar glistening gold blankets wrapped around the Apollo lunar modules or the Hubble Space Telescope. That iconic gold foil, known to engineers as Captain, served humanity beautifully for decades in the temperate orbits near Earth and the freezing depths of the outer worlds. But as BepiColombo dropped down into the sun's immediate territory, that traditional shielding became utterly useless. At this extreme proximity, the spacecraft experiences a terrifying physical force known as solar irradiance, which is simply the sheer intensity of light and thermal energy delivered by the host star onto a single unit of surface area near Mercury. This solar drenching is 10 times more powerful than anything we experience on Earth, a relentless bombardment of raw light that would bake ordinary materials, turning that famous gold foil brittle until it shattered into useless flakes of dust. To survive this blinding onslaught, the creators of BepiColombo had to discard the old rulebooks of aerospace design and invent a completely new type of armor. They crafted a magnificent, thick protective garment known as a multi-layer insulation blanket. Imagine a beautifully tailored, heavy winter coat, but instead of wool or down. This armor is composed of up to 80 individual layers of highly specialized materials, stacked loosely upon one another with thin, insulating gaps of vacuum between them. But the most striking feature of this protective suit is its color. Unlike the golden spacecraft of our youth, BepiColombo is wrapped in a garment of pure, brilliant, alpine white. This pristine hue was chosen for a profound physical reason. It reflects the overwhelming majority of the visible solar spectrum back into the void, preventing the heat from ever sinking into the metal flesh of the machine. The secret to this white armor lies in the exquisite materials hidden within its woven layers, the very outer skin of the blanket. The frontline defense against the solar furnace is woven from high-grade ceramic fibers known as Nextel, interlaced with an incredibly pure fabric made of volcanic silica called astroquartz. To the touch, this fabric feels remarkably like a heavy, durable canvas, but its chemical properties are closer to high-tech pottery. These ceramic and quartz fibers possess an astonishing thermal resilience, capable of enduring continuous temperatures of up to 650 degrees Celsius without melting, tearing, or losing their structural integrity. When the fierce solar glare strikes this outer layer, the ceramic and quartz strands act like millions of microscopic mirrors, scattering the incoming light photons in every direction, neutralizing the sun's weapon before it can penetrate the deeper layers. As we look beneath this rugged outer canvas, the inner layers of the blanket reveal an even more delicate engineering strategy. Each of the subsequent layers is separated by a tiny spacer material, creating a series of miniature thermal barriers, because heat cannot easily travel across a vacuum without a physical medium to conduct it. This multi-layered design suffocates the thermal energy, forcing the temperature to drop drastically with every layer it attempts to pass. By the time the heat filters through the final internal layers, a temperature that was once a deadly 400 degrees Celsius on the outside is reduced to a gentle, room temperature 20 degrees on the inside. This ensures that the highly sensitive scientific sensors, the advanced computers, and the delicate wiring grids remain perfectly cool and operational, resting safely in a dark, climate-controlled sanctuary while the outside world burns. We have admired the white ceramic blanket that guards the ship from the outside, reflecting the blinding brilliance of the sun. Now, let us peer deeper into the internal anatomy of the European planetary orbiter to discover a marvel of fluid engineering. Even with the finest armor, the sensitive scientific computers and advanced sensors inside the ship generate their own internal warmth as they process data. In the unforgiving vacuum of space, where there is no air to carry heat away, this internal warmth can quickly accumulate, threatening to cook the electronics from the inside out. To solve this, the designers did not install loud, vibrating fans or heavy mechanical refrigerators. Instead, they woven a magnificent, silent network of metal vessels throughout the ship's frame, creating a fluid circulatory system that mimics the quiet, life-sustaining blood vessels of the human body. This hidden labyrinth is composed of dozens of carefully routed aluminum and copper tubes, completely sealed and shielded from the vacuum outside. Inside these metallic veins flows a specialized thermal fluid, pure liquid ammonia. Ammonia possesses an extraordinary capacity to absorb and transport vast amounts of thermal energy through the simple alchemy of changing its physical state from liquid to gas. The system is designed as a continuous, closed loop that connects the hottest internal components of the spacecraft directly to the cold, dark radiator plates on the shaded side of the vessel, where an electronic instrument or a camera sensor begins to warm up. The liquid ammonia waits in a small reservoir, quietly absorbing that excess heat until the liquid reaches its boiling point, transforming gracefully into a warm vapor. This vapor naturally expands and rushes through the sealed tubing, carrying the thermal burden away from the ship's delicate core. It travels toward the outer edge of the spacecraft, arriving at the massive radiator panel that constantly faces the absolute zero cold of deep space. Here, in the shadow of the ship, the ammonia vapor releases its trapped heat into the freezing void. As it cools down, the gas undergoes a beautiful condensation, turning back into a chilled, calm liquid, ready to begin the cycle all over again. It is a continuous, looping journey of evaporation and condensation, a silent tide moving back and forth within the walls of the machine, keeping the inner sanctuary of the spacecraft at a perfect, stable room temperature of 20 degrees Celsius. The true mechanical genius of this plumbing system lies in how the fluid moves through the loops. In our cars or homes, moving fluid through a cooling system requires a mechanical pump with spinning impellers, electric motors, and seals that can eventually wear out or leak over time. But BepiColombo is on a journey that spans decades, operating millions of miles away from any repair shop. A single, broken pump would mean the immediate death of the entire mission. To eliminate this risk, the engineers abandoned mechanical pumps entirely. Instead, they designed the system to rely solely on capillary pressure action, which is simply the natural, unforced wicking power that pulls a liquid through microscopic, porous structures using the subtle forces of surface tension, completely eliminating the need for a single moving part or electrical motor. Inside the heating zones of the tubes, the engineers installed a specialized porous metal wick made of sintered nickel powder, containing channels so microscopic they can barely be seen under a laboratory lens. When the ammonia evaporates at the hot end, it creates a subtle pressure difference across this tiny metal sponge. This pressure drop behaves like an invisible, tireless straw, drawing the cold liquid ammonia back from the radiator plates with absolute unyielding consistency. It is a self-sustaining loop, driven entirely by the laws of thermodynamics. As long as there is heat at one end and cold at the other, this fluid heart will beat forever on its own, operating with the absolute silence and reliability of a mountain stream flowing downhill. Yet, absorbing heat from the instruments is only half the battle. In the grand architecture of the cosmos, a spacecraft cannot simply destroy heat. It must find a way to cast it out into the vast, dark emptiness of the universe. On Earth, we take for granted the invisible air around us, which sweeps away warmth through a gentle breeze. But in the stark vacuum of deep space, there is no air, no wind, and no medium to conduct warmth away. The only way to cool down is to use the emptiness of space itself as a giant, infinite dumping ground for energy. To accomplish this, the engineers constructed a massive, specialized component. On one entire side of the European planetary orbiter, a giant radiator panel. This panel is a flat, expansive sheet of highly polished aluminum, lined with specialized mirrors designed to look away from the sun and into the deepest, coldest corners of the night sky. The operation of this panel relies on a fundamental principle of physics known as thermal radiation emission, which is the natural process by which a physical object cools itself down by releasing its internal heat energy in the form of invisible infrared light waves, casting that energy away into the freezing vacuum of space. As the warm ammonia vapor passes beneath this large radiator panel, it transfers its thermal burden to the metal plate, which silently transforms that heat into invisible light, whispering it away into the deep dark. However, operating a giant radiator so close to the sun involves a terrifyingly strict rule of geometry, the law of the absolute shadow. For this cooling panel to work, it must remain completely and entirely hidden from the sun's glare. If even a single stray ray of sunlight were to strike the surface of the radiator, the panel would instantly transform from a cooling mechanism into a devastating thermal collector, absorbing thousands of degrees of solar energy and sending it directly into the heart of the ship, incinerating the electronics within seconds. Therefore, the entire spacecraft must be flown with absolute, unyielding discipline. keeping the radiator side permanently turned toward the absolute zero cold of deep space. Frozen in a state of perpetual darkness. This demand for perfect orientation creates a fascinating dance of angles. As the spacecraft travels along its path in this current year of 2026, its navigation computers must calculate its posture with a precision that defies human imagination. The ship must maintain what engineers call a glint-free angle, even as the planet Mercury tugs at the craft and the sun's gravity warps its trajectory. The radiator must never tilt even a fraction of a single degree toward the light. It must remain perfectly tucked away in the ship's own shadow, utilizing the bulk of the spacecraft's body as a permanent umbrella. To provide even finer control over this delicate balance, the engineers installed a series of dynamic mechanical louvers across the face of the radiator. These louvers behave remarkably like the fine wooden blinds hanging in a quiet study. When the internal computers detect that the instruments are running a bit too warm, these silver slats automatically open up, exposing the radiator to the cold void and allowing the heat to escape. If the spacecraft plunges into a temporary shadow and becomes too cold, the louvers smoothly close shut, trapping the warmth inside and acting like a thick blanket to keep the delicate electronics cozy. It is a system that responds with absolute autonomy, adjusting its metallic feathers in the dark without a single human hand to guide it. We have looked at the elegant systems of the European Planetary Orbiter, with its active liquid cooling and its massive radiator panels frozen in shadow. But sitting quietly at the very top of the mechanical tower rests the second independent scout of our journey, the Japanese spacecraft named MIO. To the engineers who built it in the quiet laboratories of Sagamihara, Japan, this satellite is a proud warrior of the East, designed to brave the invisible magnetic storms of Mercury. Yet, MIO possesses a radically different nature than its European sibling. It does not stay still. It is meant to spin like a top, rotating at a steady pace of 15 revolutions per minute to distribute the searing heat of the sun evenly across its mirror-polished body. But here lay a profound engineering dilemma during the long journey across the dark. For 8 long years of the cruise phase, MIO has been locked down completely tight, forbidden from spinning while attached to the main transport module. Without its rotation, if MIO were exposed directly to the raw glare of the solar furnace, one side would be relentlessly baked to hundreds of degrees, while the other side froze in the dark. It would be a fatal imbalance, destroying the delicate sensors before the ship ever reached its destination. To save this silent warrior from a fiery grave during its years of dormancy, the engineers had to construct a specialized sanctuary, a brilliant cone-shaped structure known as the Magnetospheric Orbiter Sun Shield, or simply MOSIF. This structure acts as a magnificent thermal insulative shield, which is simply a highly advanced barrier designed to entirely block and isolate the transfer of extreme environmental heat from the Arussilua outside world, preventing it from penetrating into the highly sensitive and delicate internal architecture of a resting spacecraft. Imagine a giant, high-tech thermos flask made of lightweight titanium and specialized ceramics, completely enclosing the Japanese satellite like a protective cocoon or a secure garage. The outside of this cone is lined with highly reflective mirrors and white ceramic fabrics that face the blinding solar rays, bouncing the destructive energy back into the void. Inside this structure, there is only the pristine, untouched vacuum of space, creating an absolute dead zone for heat transfer. There is an incredible, old-school mechanical beauty to how this shield operates. It does not use any electricity. It requires no fluid lines. And it has no complex software to fail. It protects its passenger through pure material excellence and geometric design, while the transport module below fights the gravity wells and the European orbiter coordinates the communications. MEO rests in complete and utter darkness inside this protective shell. The temperature directly outside the MOSIF cone can soar to terrifying extremes, hot enough to melt lead, yet just a few inches away, inside the quiet sanctuary of the shield, MEO remains perfectly preserved in a cool, dark, and tranquil environment, as if it were still resting in a clean room on Earth. As we look upon the mission in this current year of 2026, this silent partnership is nearing its grand conclusion. For nearly a decade, the MOSIF shield has performed its quiet duty without a single complaint, keeping the Eastern Warrior safe through billions of miles of travel. But this coming November, when the spacecraft finally enters the orbit of Mercury, this protective cocoon will have fulfilled its life's work. In a beautiful pre-programmed mechanical sequence, the shield will split open and release its passenger into the void, letting MEO emerge completely unharmed, ready to begin its spinning waltz through the planet's magnetosphere. Having survived the brutal white-hot trials of the solar forge, our cool and undisturbed traveler is finally ready to fulfill its true destiny. This extraordinary armor was not built merely for survival, but to unlock a treasure trove of deep cosmic history. As the shields hold the fiery elements at bay, the scientific eyes of BepiColombo begin to open, ready to peel back the ancient mysteries of this scorched, enigmatic iron world. From the outside, this lonely world presents a deception of familiarity, looking remarkably like our own moon, with its rolling grey plains and thousands of ancient impact craters. But this battered exterior is an exquisite illusion. Deep beneath its rocky crust lies a magnificent freak of planetary nature, a world that completely defies our classical understanding of how rocky planets are born. Mercury is, at its heart, an impossible iron ball wrapped in a deceptively thin shell of stone. In a standard rocky planet like our own Earth, the dense iron core sits at the very center as a modest, well-proportioned heart, surrounded by a massive, thick mantle of silicate rock that makes up the vast majority of the planet's volume. But Mercury completely rewrites the laws of celestial anatomy. Its metallic core is a monstrous, overwhelming entity, occupying a staggering 85% of the planet's entire radius. To grasp the sheer strangeness of this proportion, imagine an avocado where the hard, inner pit has become so unnaturally swollen that it leaves only a paper-thin layer of green flesh beneath the outer skin. It is the most iron-rich body in our entire solar system, possessing a density so immense that it has stood as a towering puzzle for geologists for generations. This disproportionate architecture presents a brilliant scientific paradox. According to the established models of how our solar system formed from a swirling disk of dust and primordial gas billions of years ago, a planet of this composition simply should not exist. The materials spinning closest to the young sun should have settled into a much more balanced mixture of rock and metal. The fact that Mercury is nearly all metal means that something incredibly violent, extraordinary, or mysterious, occurred during its early childhood to completely strip away its rocky mantle. To explain this grand planetary mystery, the scientific community has put forward several fascinating theories, each reading like an epic biography of a battered cosmic survivor. The most prominent explanation is the giant impact hypothesis. This theory suggests that billions of years ago, Mercury was a much larger, fully proportioned proto-planet with a normal, thick rocky mantle, much like Mars or Earth today. However, during the chaotic pinball era of the early solar system, a rogue planetoid, roughly one-third its size, smashed into young Mercury in a catastrophic, high-speed collision. The sheer, unfathomable violence of the impact shattered and blasted the lighter, rocky outer layers away into deep space, leaving behind only the heavy, dense iron core, which slowly recollected the remaining debris to form the stunted, metallic world we see today. Another elegant theory looks to the ancient sun itself for answers. During its infancy, our host star was incredibly volatile, prone to terrifying outbursts of superheated energy. Some scientists believe that the intense heat and furious solar winds of the early sun quite literally baked Mercury to a crisp, vaporizing its outer rocky crust and blowing the rocky vapor away into the void, leaving an exposed metallic heart behind. A third theory suggests that the friction of the early solar nebula naturally dragged heavier iron particles together while sweeping lighter rocks away. For decades, humanity could only guess which of these violent histories was the truth, but in this current year of 2026, as BepiColombo prepares to slip into its permanent home around Mercury this coming November, we stand on the absolute threshold of an answer. The European Planetary Orbiter carries a suite of highly advanced scientific instruments designed to act like a cosmic X-ray machine. It will utilize a high-precision laser altimeter and a sensitive radio science experiment to map the planet's gravitational field with absolute perfection. By measuring the subtle variations in gravity as the spacecraft glides over the surface, scientists will be able to determine the exact shape, size, and state of that massive iron core. Is it completely solid, or does it hold a churning liquid ocean of molten iron? Furthermore, the ship's spectrometers will analyze the chemical composition of the remaining rocky crust. If a giant impact stripped the planet, the remaining rock will bear specific chemical scars. If the sun vaporized the surface, an entirely different chemical signature will be left behind. For decades, planetary scientists thought they had Mercury completely figured out. It seemed obvious that a planet sitting so close to the roaring solar furnace would be entirely baked dry, stripped of any delicate or fragile materials. In the grand textbooks of the late 20th century, Mercury was routinely described as a sterile, chemically simple world, an iron core covered by a layer of scorched, inert rock. But science has a magnificent way of humbling our assumptions. And the modern exploration of this planet has revealed a profound chemical puzzle that has completely overturned the old guard of planetary science. This great puzzle centers on a specific class of materials known as volatile elements, which are simply those chemical elements and compounds, such as sulfur, potassium, sodium, and chlorine, that evaporate and turn into gas at relatively low temperatures. In our everyday experience on Earth, we know how easily water evaporates on a warm day, or how alcohol vanishes from an open bottle on a cosmic scale. These volatile elements are the delicate, fragile pieces of the planetary puzzle. The established scientific consensus held that because Mercury was born in the white-hot heart of the early solar system, these delicate elements should have been boiled away billions of years ago. It was assumed that Mercury was a world entirely devoid of volatiles. But in the early years of the 21st century, a robotic messenger sent back data that sent shockwaves through university geology departments around the globe. When scientists analyzed the first close-up chemical scans of the planet's surface, they did not find a world stripped bare by the sun. Instead, they discovered an absolute abundance of volatile elements scattered across the grey, cratered plains. The surface was rich in sulfur and potassium, elements that should have vanished long ago if the planet had ever experienced extreme, catastrophic heating. This is the great volatile paradox of Mercury. It is a planet that possesses a monstrously heavy iron core, which usually indicates a violent, high-energy past. Yet its surface is covered in fragile, heat-sensitive elements that could only survive in a much cooler, gentler environment. Finding these elements on Mercury was the scientific equivalent of opening a roaring blast furnace and discovering a delicate wax candle sitting completely unmelted in the center of the flames. It was an impossible reality that shattered our neat, orderly models of how the solar system was constructed. This single discovery instantly dealt a fatal blow to the classic theories of Mercury's birth that we discussed earlier. If a giant cosmic collision had smashed into the young planet and blasted away its outer mantle, the unimaginable heat of that impact would have instantly vaporized every single atom of sulfur and potassium, casting them permanently out into the void. Likewise, if the intense radiation of the early sun had baked the planet's crust into vapor, these volatile elements would have been the very first things to disappear. The fact that they are still there, integrated into the dark soil of the planet, means that our old stories about Mercury are fundamentally wrong. It suggests that Mercury could not have been formed through a history of brutal violence. Instead, it hints at a far more mysterious origin story. Perhaps the planet was born much further out in the cold, dark rims of the solar system, where volatiles were plentiful, and was gently nudged inward by gravitational currents later in its life. Or perhaps the primordial dust cloud surrounding our young sun accumulated into planets through a much more quiet, cold, and gradual process than we ever dared to imagine. To solve this fascinating cosmic riddle, BepiColombo arrives at its destination in this current year of 2026, carrying an arsenal of highly advanced scientific eyes. The European Planetary Orbiter is equipped with state-of-the-art spectrometers, including the Mercury Imaging X-ray Spectrometer and the Mercury Radiometer and Thermal Infrared Spectrometer. These instruments do not merely photograph the landscape, they read the elemental barcode of the dirt itself. As the spacecraft glides through its permanent orbit this coming November, these sensors will bounce light and radiation off the surface, mapping the exact distribution and concentration of these volatile elements across the entire globe. By determining whether these materials are hidden deep within ancient volcanic vents or spread evenly across the cratered plains, BepiColombo will provide the final, definitive clues needed to rewrite the biography of our solar system. Let the deep, comforting quiet of the night carry us away from the blistering heat of Mercury's equator and up toward its silent, forgotten poles. Here, at the very crown of this iron world, we encounter perhaps the most staggering paradox in all of planetary science. If you were to ask any ordinary man where to look for water ice in our solar system. The very last place he would point is this sun-scorched rock. It is a world that can reach temperatures hot enough to melt lead at its midsection, a place completely drenched in the blinding fury of our host star. Yet, tucked away in the deep northern and southern rims of this planet lies a treasure trove of pure, frozen water ice, preserved in absolute darkness for billions of years. To understand how ice can exist in this cosmic kiln, we must look at the unique tilt of Mercury's axis. Unlike our Earth, which tilts at a comfortable angle of 23 degrees to give us our changing seasons, Mercury stands almost perfectly upright relative to its path around the Sun. Its tilt is virtually zero. Because of this perfect vertical posture, the Sun never rises high in the sky at the planet's poles. Instead, the solar disk skims horizontally along the horizon, casting incredibly long, dark shadows across the landscape. Any deep crater sitting at the poles creates a permanent sanctuary of darkness, a phenomenon known as a permanently shadowed region, or a cold trap. A cold trap is simply a deep geological depression near a planet's pole where the sun never shines, causing temperatures to remain permanently frozen at over 200 degrees below 0 Celsius, creating a perfect cosmic refrigerator capable of trapping and preserving volatile compounds like water ice forever. For a long time, the idea of ice on Mercury was merely a beautiful mathematical theory whispered in university hallways. But in the early 1990s, scientists fired powerful radar signals from the massive Arecibo Observatory in Puerto Rico, bouncing radio waves off Mercury's poles. The signals returned to Earth with a brilliant, highly reflective signature that stunned the scientific community. It was a reflection that could only be caused by vast sheets of pure water ice. Years later, NASA's Messenger spacecraft confirmed these radar findings, discovering that these dark craters indeed held vast reservoirs of ice, hidden beneath a mysterious thin layer of dark organic dust. Yet those early missions could only give us a flat, two-dimensional glimpse from a distance. They could tell us that ice was present, but they could not reveal its true shape, its thickness, or how it interacted with the rugged terrain of the crater floors. In this current year of 2026, as BepiColombo draws near its final orbital capture this coming November, we stand on the precipice of a mapping revolution. The European Planetary Orbiter carries a crowning jewel of optical and physical engineering, the Mercury laser altimeter, working in perfect unison with a suite of advanced infrared cameras. As the spacecraft glides over the polar rims in its tightly bound orbit, it will perform a task that has never been achieved before, building a complete, high-resolution, three-dimensional map of these hidden ice sheets. The laser altimeter operates by firing rapid, precise pulses of light down into the pitch-black void of the cold traps, measuring the exact fractions of a second it takes for the light to bounce back from the frozen surface below. By analyzing thousands of these laser pulses every single minute, the onboard computers will reconstruct the true topography of the ice. We will finally see the exact thickness of these frozen oceans, mapping every ridge, every crevice, and every slope in 3 dimensions. This three-dimensional mapping will do far more than satisfy our cartographic curiosity. It will help solve a grand historical mystery regarding the origin of our solar system's water. By knowing the precise volume of the ice and analyzing the dark, carbon-rich materials covering it, scientists can deduce where this water came from. Did it arrive billions of years ago on the backs of icy comets that smashed into the young planet? Or did it bleed out from the interior through ancient volcanic outgassing? For generations, men of our vintage have admired the predictable gears of classical machinery. We once understood the universe through these classical mechanics, where time flowed at a constant rate and gravity was a simple pulling force. But over 100 years ago, Albert Einstein completely shattered that comfortable paradigm with his masterpiece, the theory of general relativity. He taught us that space and time are not a rigid stage upon which the celestial dance occurs. Instead, they are woven together into a single, flexible fabric, a cosmic grid that is stretched, bent, and warped by the weight of massive stars. To visualize this profound truth as you relax tonight, imagine a tightly stretched trampoline. If you drop a massive bowling ball into the center, the fabric sags dramatically, creating a deep, sloping bowl. If you then roll a small marble around the edge, it spirals gracefully along the curved slopes of the indentation. In our solar system, the sun is that monstrous bowling ball, warping the very geometry of the space and time surrounding it. Because Mercury sits directly on the steepest slope of this gravity valley. It serves as the absolute premier natural laboratory to test whether Einstein's wild vision holds true under the most extreme conditions imaginable. For decades, astronomers noticed a strange quirk in Mercury's behavior that classical physics simply could not explain. Every time the planet completed its orbit around the Sun, the point of its closest approach, known as the perihelion, shifted by a tiny, inexplicable fraction of a degree. It was as if the entire orbital loop was slowly rotating in space. Newton's equations failed to account for this extra drift. It was only when Einstein applied his mathematics of warped space-time that the mystery was solved. The curvature of space near the Sun was so intense that it altered the path of the planet. Einstein's field equations dictate a beautiful relationship where matter tells space-time how to curve, and curved space-time tells matter how to move. In the intense vicinity of our host star, this relationship becomes a visible, measurable reality. Now, in this current year of 2026, BepiColombo is poised to push this testing to an unprecedented level of precision. The European Planetary Orbiter carries a crowning achievement of radio engineering known as the Mercury Orbiter Radio Science Experiment. As the spacecraft glides through its permanent orbit this coming November, it will engage in a continuous, invisible dialogue with deep space tracking antennas back on Earth, sending ultra-precise radio signals back and forth through the distorted space surrounding the Sun. This sophisticated experiment will look for a phenomenon known as the Shapiro time delay. When the radio signals travel from the spacecraft to Earth, their path must cut directly through the warped space-time valley created by the Sun. Because the fabric of space is stretched, the radio waves must travel a slightly longer distance. And because time itself slows down near a massive gravity source, the signal arrives on Earth a fraction of a millisecond later than it would in flat space. By measuring these microscopic delays down to a precision of mere centimeters over a distance of millions of miles, the tracking system will verify Einstein's equations with an accuracy 10 times greater than any previous mission. It will measure the exact curvature of the cosmic fabric, checking for any tiny, elegant deviations that might hint at new, undiscovered laws of physics. or perhaps confirm our current understanding with absolute certainty. To transform these grand scientific ambitions into definitive textbook chapters, the mission must now answer its final calendar appointments. The long, patient years of deep space cruising are drawing to a close. As we look toward the rapidly approaching horizon of November 2026, we transition from the quiet anticipation of the voyage to the dawn of historic discovery, marking the definitive arrival of our silent vanguard. In the spring of 2024, far out in the blinding glare of the inner solar system, BepiColombo faced its darkest hour, a quiet, creeping crisis that threatened to leave the entire mission stranded forever in a permanent graveyard around the sun. It began in April of 2024. The engineering teams at the European Space Operations Center in Darmstadt, Germany, noticed a sudden, chilling drop in the electrical current flowing from the spacecraft's massive solar arrays to its vital ion thrusters. This was not a minor glitch. It was a profound technical failure. The bold ion engines, which require a massive amount of electricity to accelerate those heavy xenon atoms into a steady braking stream, were suddenly starved of their lifeblood. The spacecraft's muscle was crippled, operating at only a fraction of its intended capacity. In the unforgiving lexicon of deep space operations, this event was classified as a spacecraft power distribution anomaly, which is simply a disruptive failure in the electrical circuitry where a malfunction in the onboard isolating diodes prevents the collected solar energy from fully reaching the main propulsion systems, leaving the vessel unable to generate the necessary thrust to maintain its pre-calculated trajectory. To the veteran engineers on Earth, this was a nightmare scenario. Without full power from the ion engines, BepiColombo could no longer execute the massive deceleration maneuvers needed to slow down its approach to Mercury. It was sliding down the steep slope of the sun's gravity well with no brakes, heading toward a permanent overshoot in an earlier era. Such a devastating blow might have triggered panic, a flurry of desperate commands that could have broken the ship entirely. But these engineers possessed the patient, unhurried grit of master craftsmen. They did not rush. They sat in the quiet of their control rooms, rolled up their sleeves, and began to analyze the telemetry line by line. For months, the tracking teams worked in absolute silence, rewriting the software code and completely redesigning the remaining years of the flight path. They accepted that the ion thrusters would never return to full strength. Rather than fighting this unyielding reality, they decided to turn it to their advantage. They calculated a brilliant, highly sophisticated detour. By lowering the thrust requirements and utilizing the natural gravitational currents of the inner planets with even greater precision, they could still guide the ship to its destination, but it would require an encounter of breathtaking, white-knuckle proximity. This calculated gamble culminated on the 4th of September in that same year of 2024. The crippled explorer approached Mercury for its fourth critical flyby. The flight path was so daringly low that it left absolutely no margin for error. As the world below held its breath, BepiColombo silently plummeted toward the rugged grey plains of the innermost planet. The spacecraft performed an absolute miracle of celestial navigation, skimming just 165 kilometers above the scarred, cratered surface of Mercury. To put that into perspective, this is a distance closer than a casual weekend drive between two neighboring American cities, executed while moving at a blistering speed of several kilometers per second through the frictionless void. It was the closest any human machine had ever dared to glide past this hostile, sun-baked world. As the ship swept through this ultra-low corridor, its simple monitoring cameras blinked open, capturing spectacular, high-definition, black-and-white images of the rugged landscape below. They revealed the immense tectonic cliffs, the ancient, shattered impact craters, and the vast volcanic plains rolling beneath the ship's belly like a ghostly, silent movie. The spacecraft was so close that it could feel the subtle, uneven tug of the planet's internal mass variations. By successfully executing this legendary 165-kilometer skim, the mission achieved a double victory. Not only did it gather priceless scientific data from the absolute closest vantage point in history, but it also used Mercury's own gravity to bleed away the exact amount of excess speed that the broken ion engines could no longer handle. The planet itself had acted as the ultimate brake, catching the wounded traveler in its arms and nudging it safely back onto the correct path. For anyone who has ever spent a long day behind the wheel of a heavy machine or guided a fine vessel across a vast body of water, there is a singular, unforgettable feeling that comes at the very end of the haul. It is that precise instant when you finally take your foot off the accelerator, ease the throttle back to idle, and let the sheer, magnificent momentum of your vehicle carry you the rest of the way home. In this very year of 2026, our silent, deep space explorer has just reached that exact milestone. This past June, far out in the blinding white glare of the inner solar system, BepiColombo executed a quiet command that brought a historic era of space exploration to its magnificent conclusion. For nearly 8 long years, the Mercury transfer module has served as the tireless, brave heart of this expedition. Day after day, its sophisticated electrostatic ion thrusters have emitted a faint, ghostly blue glow, releasing a steady stream of charged xenon atoms to act as a relentless cosmic brake. It was a marathon of engineering endurance that spanned billions of miles through the dark. But on a quiet day this past June, the final pre-programmed deceleration sequence came to an end. The electrical currents harvested from the massive solar arrays were gently stepped down, and the intake valves regulating the titanium xenon tanks were closed tight. For the first time since leaving its launch pad on Earth, the soft, ethereal blue light at the base of the craft faded into the blackness of the void. The engines were officially powered down for the very last time. This milestone marks the definitive transition into a beautiful phase of navigation known to aerospace engineers as inertial coasting, which is simply the passive, unpowered phase of a spacecraft's journey where all active propulsion is ceased, leaving the vehicle to glide gracefully through the vacuum of space, relying solely on its existing momentum and the natural gravitational currents of the surrounding celestial bodies. Without the active whisper of its ion engines, the spacecraft is no longer fighting the cosmos. It has surrendered its path completely to the elegant, unyielding laws of Sir Isaac Newton. It is no longer an active machine pushing its way through the dark. It has become a silent passenger of the gravity well, floating with absolute grace toward its final destination. To appreciate the calm majesty of this phase, imagine a classic timber yacht returning to port after a long, grueling race across the open ocean. As the vessel enters the quiet waters of the harbor, the skipper drops the heavy canvas sails, cuts the rumbling diesel engine, and allows the boat to glide silently toward the wooden pier on nothing but its own smooth, accumulated momentum. The water laps softly against the hull as the vessel slows down naturally, perfectly balanced and entirely at peace. This is exactly how BepiColombo is traveling right now in this month of July. It has spent nearly a decade doing the heavy, exhausting work of braking against the immense pull of the sun. Now, that work is finished. The ship is coasting on pure, unforced inertia, falling gently toward the waiting arms of Mercury. This period of unpowered drifting is not a time of lawlessness, but a display of ultimate mathematical precision. The navigational teams on Earth calculated this trajectory years in advance, ensuring that the velocity remaining after the engines fell silent would be exactly right as the spacecraft glides through the remaining miles of the void. The planet Mercury is rising up from behind, moving along its own orbital track like a perfect clockwork gear. The two entities are closing the distance between them, not with a violent collision, but with the gentle, synchronized movement of two ballroom dancers approaching a final embrace. Every mile the ship travels brings it closer to its ultimate capture this coming November, when the natural gravity of that iron world will permanently cradle the explorer into its loop. There is a profound, meditative lesson to be found in this phase of the voyage. It reminds us that there is a time for striving, a time for burning fuel, and a time for pushing against the currents of life. But it also reminds us that there comes a moment when the best thing we can do is to simply let go, to power down our internal engines, and to trust in the steady, orderly forces that guide our path through the dark. Let the quiet darkness of the evening settle deep into your thoughts as we peer over the final horizon of this epic journey. We are currently sitting in this year of 2026, watching our traveler glide silently on pure, unpowered inertia. But as the calendar turns to the crisp dawn of 2027, this quiet prelude will give way to a golden age of discovery, following the grand separation and orbital insertion this coming November. The year 2027 will mark the official commencement of the nominal science mission, a period where the two independent scouts will finally unveil the ancient secrets of the iron world. For men who appreciate a job well done, this is the moment where the long, patient years of investment finally pay off. The decades of planning, the billions of kilometers traveled, and the trials of the solar forge have all been leading to this precise window of time. Throughout 2027 and into 2028, Mercury will be subjected to the most intense, unblinking scientific scrutiny in human history. The two satellites will operate in perfect, synchronized harmony, though their paths will be entirely different. The European planetary orbiter will trace its low, tight, circular loop, skimming just hundreds of kilometers above the solid rock. It will utilize its advanced array of cameras and spectrometers to build a complete three-dimensional map of the surface, reading the chemical barcode of the cratered plains and measuring the exact size of that swollen iron core. Simultaneously, the Japanese satellite, MIO, will loop through its wide, sweeping elliptical orbit further out in space, spinning steadily at 15 revolutions per minute. MIO will feel the invisible currents of the planet's magnetosphere, tracking the violent streams of solar wind as they clash with Mercury's magnetic shield. Together, these two machines will send a relentless torrent of data back across the vast gulf of space to our waiting radio dishes on Earth. This information will be dissected by generations of scientists, effectively rewriting the textbooks on how our solar system was constructed. But, as any practical man who has managed heavy machinery knows, Even the finest engineering cannot endure a hostile environment forever. The territory near the Sun is a brutal, unrelenting forge. Day after day, the intense solar radiation and the scorching heat will take a steady toll on the spacecraft's physical frame. The pristine, white ceramic blankets that protected the ship during its journey will slowly begin to degrade and discolor under the constant bombardment of cosmic rays. The highly sensitive electronic brains inside the cool wood fluid-filled chambers will gradually accumulate microscopic scars from the relentless solar flares. The mission teams in Europe and Japan will squeeze every single ounce of utility out of the instruments. If the hardware remains stable, the operations will be granted a well-deserved extension, pushing the science phase deep into the following years. But the architects of the mission have always known that an absolute limit exists. This limit is not determined by a failure of the computers, but by the finite supply of chemical propellant stored within the ship's small attitude control tanks. To keep the European craft's massive radiator panel locked safely within the absolute shadow, tiny thrusters must fire short, meticulous puffs of gas with absolute consistency when those fuel tanks finally run completely dry. The strict geometric discipline that kept the ship cool will be permanently lost. The radiator will inevitably tilt toward the blinding solar glare, and the spacecraft will gracefully conclude its active scientific life. Yet, BepiColombo will not be left to drift as a forgotten piece of space junk. The engineers have designed a finale that is just as poetic and purposeful as the journey itself. They have choreographed a spectacular, deliberate final act, the grand epic plunge. When the final drop of propellant is reached, the flight controllers on Earth will send one last sequence of commands. The European planetary orbiter will use its remaining breath to lower its altitude for the very last time, setting itself on a terminal, irreversible trajectory toward the planet below. In its final moments, the spacecraft will become a brilliant, silent shooting star across the airless sky of Mercury, moving at a blistering speed of several kilometers per second. It will dive headfirst into the rugged grey plains it spent years mapping. It will smash into the ancient crust, creating a brand new, pristine impact crater on the surface of the iron world. In that single, ghostly millisecond of impact, the titanium framework, the white ceramic fabrics, and the exquisite glass optics that human hands built with such devotion will instantly vaporize, merging permanently with the primordial dirt of the planet. There is a magnificent, profound symmetry in this ending. The explorer does not abandon its target. It becomes a permanent part of it. The materials we took from the Earth to build this machine are returned to the soil of another world, leaving a permanent monument to human curiosity written directly into the geology of Mercury. As our journey through the scarred landscapes and fiery trials of Mercury comes to a close, we find ourselves returning to the grand, overarching theme of this cosmic odyssey, the absolute, unbroken silence of the deep night. We have spent this hour marveling at the incredible grit of human ingenuity, the beautiful symmetry of the modular design, the brave whisper of the ion engines, and the white ceramic armor that kept the harsh glare of the sun at bay. We have looked forward to the golden age of discovery that awaits in 2027, and the poetic finale that will write our presence permanently into the Iron Planet's history. Beyond the complex machinery, the telemetry, and the historic scientific triumphs, the story of BepiColombo is ultimately a meditation on peace. It reminds us that no matter how chaotic, loud, or overwhelming our immediate world may seem, the vast majority of the universe operates in a state of pristine, untroubled tranquility. Out there, millions of miles away from our daily worries, our silent explorer coasts gracefully through the dark, entirely in tune with the grand, clockwork laws of nature. There is an immense, comforting legacy in this realization for men who have spent their lives building, doing, and protecting. True strength does not always require noise. The most profound achievements, whether it is a spacecraft mapping a distant world or a life well lived, often culminate in a state of quiet grace. The eternal silence of these infinite spaces does not frighten us. It invites us to rest. It is a gentle reminder that there is a time for the heat of the forge and a time for the cool sanctuary of the shadow. As you let the final echoes of this epic voyage fade from your mind, feel the profound serenity of that cosmic dark wrap around your own room tonight. The long journey of your day is fully complete, your obligations fulfilled, and your destination reached. The machinery of your thoughts can now be safely powered down, leaving you to drift on pure, unforced momentum. Let yourself sink deep into the quiet canvas of the night. Trust in the timeless harmony of the stars and glide effortlessly into a deep, beautiful, and restorative sleep.